So on the last couple problems, we actually finished up class yesterday, and now I am here late at night trying to wrap things up, getting ready for our big trip. And the big secret is I am sneaking my wife away on a trip to San Francisco for her 40th birthday. Her birthday's next month, but I've got all these ducks finally in a row, and I've called all the right people, and I snuck her out of school and putting her on a plane tomorrow morning. Which is 9:10 a.m. on Friday. We're flying to San Francisco for a couple of days, and something we kind of been planning ahead of time. So should be fun. She has no idea. I hope it goes well. I imagine she'll be pretty excited about it. So in the meantime, you guys are slaving away. I hope we'll be somewhere over the far western part of the state or the country, making our way to San Francisco. So see you guys all on Tuesday. But in the meantime, we left off on Thursday with just a little bit of U-substitution, and they're from that CUDA sheet. So finish that. That's where you should start. Go to that CUDA worksheet. I think I posted a key under materials on our Google Classroom for the rest of that first sheet. I didn't have it attached. On the back side, you guys have a page of practice problems that are U-substitution that have an answer next to them. So you'll figure that out. But these that I'm doing in the notes here tend to be a little more challenging than the ones you're seeing on that CUDA sheet. But the CUDA ones are kind of your standard good U-sub problems you should know. I'm showing you some more to help you build your algebra repertoire related to doing integration anyway. Okay, let's start. Example 5 it goes like this. If you want to pick a U, and there's all kinds of, oh my word, the pun potential here is amazing, but I'll try and hold off as best I can. You take a U that is inside function, and so if you're just looking for parentheses, denominator, exponent, something that would require you to do the chain rule if you're doing a derivative, that's what I mean by an inside function, then you pick it. It's usually an okay, and you're going to be safe. But you also, one of the requirements for U-substitution to work is that the derivative of that so a multiple of that must show up outside. And I know you may not think of it, but this little x right here is a multiple of 2x. It's just 2 times x. So therefore, this is a perfect U-sub problem. One of the things you want to watch out for is this problem actually has that 1 over pi might be something you want to sneak out front there. There's a lot of little algebra tricks that you got to watch out for. But my U stuff is, first off, u equals x squared plus 1. Derivative, du dx, is 2x. And when you're doing the U-substitution, the derivative in this differential notation provides the dx that's part of my integral. So it's important that we take the derivative because my integral has a dx in it. The only way I'm going to get that in the stuff in my U-substitution is if I derive u. So now I'm going to multiply both sides by dx because you need your u stuff on one side and your x stuff on the other. Now if you look at it, the problem over here on the left, I'm going to put a little red going on here, has just x dx, and I've got 2x dx. I just need to move that 2 out of there. So I'm going to divide both sides by 2. And I'm pretty much set. Okay, so I'm going to put this back together, go back to blue. It'll be like 1/2 du is how I like to write this, is equal to x dx. Now I'm ready. These are my pieces that are going to replace what my current integral looks like. So remember, the x dx is going to replace the x dx that's in the integral right now, and then the u equals x squared plus 1, let's underline that in orange, that little x squared plus 1, that's going to be replaced by u. Okay, so it's a direct swap out. Things that are equal can be traded, and the x dx, gone. All I get is if you want, I can write half and then du, kind of where the x and dx used to be. If that helps you kind of visualize this, you don't have to do that. And then instead of x squared plus 1, I put u squared. So by trading these things out, I was able to get an integral that has u's in it. If you still have x's in your integral, that means you didn't fully substitute with your u stuff. And this is way more flexible than I'm showing you right now. When I pick a u and I derive u, any manipulation of that u equation, you're welcome to trade out in the integral over here. We're just temporarily swapping things out. And that made a nicer integral. Now, it may not look like it to you. I can get that half out front, and that'd be 1 over 2 pi, because half times 1 over pi is 1 over 2 pi. Then I've got u squared du. It's a nice integral. It's just 1 over 2 pi times 1/3, or u cubed over 3 plus c. This is the point where just a little simplifying, and then I put u back. My u is x squared plus 1. So if I put it all together in my bibbidi-bobbidi-boo fashion, then I've got x squared plus 1 cubed to go back. Wait, is that right? Yeah, right above here. I'm just trying to figure out what I'm looking at. Yep, x squared, so it's cubed, plus c. The 6 pi comes from multiplying the 2 and the 3. But I'm done. That's the end-all, be-all. And my c suddenly looks a little bit like a 0. So we're going to fix that. Got it. And we're done. So that's 5. Let's jump to 6. You guys can pause and go back as needed. The next 3 kind of help you pick out the pattern, because all of them have the same u, and then just playing it out, this kind of helps you helps you find out what your, and I think it's each of the following has the same. I don't know if it's just A through C. I think the rest of them do as well. I wasn't looking that far ahead, but they all have the same u. And then you do substitution to make it happen. Let's finish with example 6, and then you guys should just go to work on your CUDA worksheet, on the worksheet that you already have, the first page of which we were mixed up on that yesterday on Thursday. Everybody started on the wrong one, probably my mistake there. But it's like the worksheet 4.3, Fundamental Theorem of Calculus. If you keep going in that packet of fun, you get to worksheet 6.4, that's integration by U-Substitution. Those are pretty tough. But I also gave you that CUDA sheet that's two-sided, and it has some nicer U-Substitution. That's all yours. And you have some time in the library, not in the library, in a computer lab that you guys can go down and work on some iMath lab. Get that cranked up and running. Okay, so now, let me talk about A, B, and C. I'm going to work pretty fast. Pause, rewind, do whatever you need to do. But we all know it's going to be u equals cosine of 2x, and then the derivative of u, du dx, is going to be, when you do it, it's a chain rule. Derivative of cosine is negative sine, but you're also going to take the derivative of the inside, so it's negative 2 sine 2x. You take the derivative of the outside, which would take cosine into negative sine, and times the derivative of the inside, so times the derivative of 2x, which shows up right there, times 2. That's our chain rule. Okay. Now if you look up here, I have, instead of negative 2 sine 2x, I got 5 sine 2x times e. And then there's this whole e business as well. I don't know about you guys, but I don't see an e yet in ours, but that's okay. Okay, so I need to change that negative 2 into a 5. Now I can divide away negative 2 on both sides and then multiply both sides by 5. The mechanics are divide away the negative 2 and then multiply both sides by 5. And also that dx needs to be on the right hand side with the x's. So watch this. I got negative 1/2 du equals sine 2x dx. Now I'm almost there. Then I'll go through and multiply both sides by 5. So this is 5 times this stuff and then 5 here. And what I've got is a nice swap for, let me highlight this in some orange right here, the 5 sine 2x right here, and the dx right here. That replaces everything but the e to the cosine 2x. And the e to the cosine 2x, I'm actually going to take my cosine 2x and trade it out for the numerator there in that, or the exponent in that e function. Okay, so that's what I'm shooting for. That's the substitution process. In that process then, see how these get multiplied here? That'd be negative 5/2 du is what I replace the 5 sine 2x dx with. And so I'm going to put in there negative 5/2, and I kind of like putting the du over the dx used to be. Okay, so I just traded out 5 sine 2x dx in the original, right here. So you see it right there. And that with negative 5/2 and du. Just traded them. That's what I got on this other side. And then I'll take on the other is I got to replace the e to the cosine 2x with e to the u. Because if you look above here, I'm going to change my pink. I'm going to go a little bit of orange up here. My cosine 2x, I get to replace with just the u function that it's equivalent to. So if you check it out, this is a lot easier. When you swap out all the x stuff for its equivalent to u expression by picking the u appropriately, then you should have a pretty nice integral. So in the end, this will just be the integral of e to the u is e to the u. So it's going to be negative 5/2 e to the u. Since this one's kind of clean, it's just going to be negative 5/2 e to my u of cosine 2x Okay, so e to the cosine 2x plus c. Done. Okay. And I'm going to get a little faster as we go. You're going to start seeing this. It gets better. I like this series of them being really similar to each other because you do get better at noticing, all right, I have the same u. It's all going to work out. This one's got some wild exponent stuff that you got to watch out for. This cosine squared 2x and to the third, or cube rooted, sorry, is the same thing as cosine of 2x quantity squared, but all to the 1/3 power. Right? That's a lot of power stuff that you have to get used to. So I'm probably going to rewrite this integral as 7 sine 2x, and then a cosine of x, or cosine of 2x, sorry, all to the 2/3. That's a little cleaner. It's easier to see what's going on. The u, again, is cosine 2x. It's an inside function whose derivative, a multiple of its derivative, is right outside. So I got cosine 2x, got it, and then du dx. Sometimes I get kind of, I jump ahead a step and I actually move the dx to the right-hand side first off. So the derivative of cosine is, of course, negative 2 sine 2x. We dealt with this before. Dx, I kind of skipped a step in between here, and I just put the dx on the right ahead of time. Now we're close. I've got a 7 over here. Currently I have a negative 2, so I want to move those out. And so I divide by negative 2 and then multiply through by 7. So can you kind of anticipate this would be negative 7 halves du equals 7 sine 2x dx? Can you kind of picture that? That's dividing by negative 2, then multiplying by 7 on both sides. And now I got a direct swap. And that's the key. We're looking for stuff we can trade out. Bam, that 7 sine 2x matches here. Of course, the dx comes out. And the substitution can move forth. I can do, now I've got the integral of negative 7 halves of du. I'm going to put it on the other side where dx used to be. And that replaces those. And instead of cosine of 2x to the 2/3, I'm going to do u to the 2/3. Okay, and I'm going to replace, so if you're looking for where that came from, oops, missing my colors today, that cosine of 2x, they replaced each other, so here they are. U to the 2/3 instead of cosine of 2x to the 2/3. And so I derive that bad boy, which means add 1 to the power. So you get negative 7 halves, and that's u to the 2/3, add 3/3 to it, so that'd be 5/3, and then divide by that. So it's u to the 5/3, and then divide by 5/3, which would be multiplying by 3/5 plus c. And when you do that, you get a pretty goofy looking antiderivative, but it's not too bad. It's negative 21/10, and then u is actually, of course, our cosine of 2x, all to the 5/3 plus c. Done. Nice? Maybe not, but hopefully it's getting a little bit better. And over and over and over again we do this. Okay, next one, same thing. You want to think of this cosine squared. This is really the same thing as cosine of 2x quantity squared. So when I do my u-substitution, u is cosine of 2x, and then du is negative 2 sine 2x, but I don't want negative 2, I actually just want positive 2, so I move the negative over. I got a nice swap right here. And then the integral then is integral of, it's going to be negative, and then instead of cosine of 2x quantity squared, it's going to be u squared dx. I'm sorry, du. Let's write the u in there. Okay. And now that I've done this, just watch for the pieces that you know. This 2 sine 2x replaced, and then by the way, I forgot, that's what it was. I forgot to put my dx in there, but that threw some folks off. There you go. Put my dx back in there, but it's right there. I replaced those with negative du. Here's the negative, and here's the du. Okay, replaced all that stuff in orange up top. And then, of course, it's u squared. Replaces the internal part of it. Finish it off, and we have a, need a divider line here, negative 1/3 u cubed plus c. Put the u back, and we've got negative 1/3 cosine of 2x cubed plus 3 plus c. There it is. That's our next, that was our 3 in a row. That's enough for today. We can get back on Tuesday, but that'll give you a head start. And it'll also give you enough time to go down to the lab and do a little work on that My Math lab. Enjoy the day. Thanks for all your hard work. Back out of this thing a little bit, see if I can get the video stop.